Hello and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 30 in the series, Simplifying Radical Expressions. So before we dive in, let's review some of the patterns in fractions that will lie at the heart of simplifying radicals. Specifically, we need to recall how we reduce fractions and how we construct mixed numbers. So remember, if the top and bottom of a fraction have a common factor, we can cancel after we factor it out and get a reduced fraction. In this case, 6/9 has a common 3 in the top and bottom, and after factoring the 6, factoring the 9, and canceling the common 3, we get 2/3. And if the numerator is greater than the denominator, we can rewrite it as a mixed number. So let's recall how to do that and what it means. Let's say we wanted to reduce 9/4. So 9/4, if we divide 9 by 4, we get 2 with 1 as a remainder. And that means we can write 9/4 as 2 plus 1 over 4. And often this is just written without the plus symbol, 2 and 1/4, but you hear the and in there telling you that there really is a plus between these two. They are not being multiplied in a mixed number. Another way that we can see this is the case is that if I were to multiply on both sides by 4 here, that is to say, if I had 9 divided by 4 is 2 remainder 1, then what this really means is that 9 is equal to 4 times 2 plus 1, right? 8 plus 1 is 9. And if we'd like, we could divide on both sides by 4, go back to where we started, and we have 9/4. Distributing the 1/4 or the dividing by 4 against these two terms cancels to give me a 2 and persists to give me 1/4. So that's how we can arrive at this expression. Now let's see what this means as far as radicals are concerned. We're going to be able to apply this kind of stuff to radicals because radicals are really just fractions in the exponent. So recall that the b root of x to the a could be rewritten as a fraction power x to the a over b. The index becomes the denominator, and this power becomes the numerator. So if I have something like the fourth root of x to the 8, then this is x to the 8/4. 8/4 is fancy talk for 2. So really, this whole radical expression here just turns into x to the 2, or x squared. Here's another one that doesn't reduce all the way to an integer like that one did. What if I wanted to take the 9th root of x to the 6th? Is there an easier way to write that? Yeah, because there's an easier way to write 6/9. 6/9 reduces to 2/3, as we saw. This is the third root of x squared, or the cube root of x squared. So this expression with larger numbers can be rewritten as one with smaller numbers by taking advantage of how we reduce fractions. So what about this mixed numbers thing then? What about if the power inside the radical, the so-called radicand, the argument of the radical, what if that guy is bigger than the index of the radical? And we have this improper fraction over here. Well, since 7/3 could be rewritten as 2 and a third, right? 3 goes into 7 twice with 1 remainder. Then we could actually rewrite x to the 7/3 as x to the 2 plus 1/3. Plus, in the exponents, is timesing between the bases. And now look, we have a proper fraction, lower numerator than denominator, over here now. So let's rewrite this back in radical notation, and this just says x squared times the cube root of x. And this is a, maybe not simpler in terms of the economy of symbols, but this is simpler in terms of lower numbers, smaller quantities, way to write this radical expression. Now, it's worth noting, because exponents distribute, radicals are also going to distribute, because radicals are just fractional exponents. They're just another kind of exponent. So they do all the things that exponents also do. And let's be clear, I mean distribute around multiplication and division. We talked about how exponents don't distribute around addition and subtraction, and that means that radicals won't as well, right? We can't write the square root of x plus y as the square root of x plus the square root of y. That's wrong. So, but we can, however, distribute it around multiplication like this, and we can distribute it around division like this. Now, why would you want to do such a thing? Well, because instead of thinking about this complicated argument we could think about two simpler arguments, two simpler expressions, but then put those into the top and bottom of a fraction, or put those side by side in a product. So now let's take a look at a numerical example expressing this idea. What is the square root of 9/4? Now, we don't want to think to ourselves, what's the square root? What times itself is equal to 9/4? No, don't worry about that. Just think to yourself, what's the square root of the numerator? What's the square root of the denominator? 3 times 3 is 9, so the square root of 9 is 3. 2 times 2 is 4, so the square root of 4 is 2. And that means that the square root of 9/4 is 3/2. And yes, if you multiply 3/2 by 3/2, you do get 9/4. How about this one? So in this case, what is the cube root of 8 times x to the 8? So what we want to do here is we don't want to treat this as one big block. We want to split it up using distribution and take a look at these two problems separately. So here's them separated. What is the cube root of 8? Well, that's just the question, what times itself 3 times is 8, and 2 times 2 times 2 is 8, so the cube root of 8 is 2. How does this guy, the cube root of x to the 8, how does that simplify? Well, this is x to the 8/3. That's the exponential form of this radical expression. 8/3 is 2 and 2/3. Divide 3 into 8 and get 2 with remainder 2. And then this can be split up by multiplication. Multiplication of the bases is addition of the exponents. And so we get 2x's coming out. You might notice this quotient here is coming out as the exponent here. And the remainder here is getting stuck inside, right? 2/3, now a proper fraction, puts x squared inside of a cube root. So we put those two together and say, well, then we just take their product, and that's 2 times x squared cube root of x squared. And this is our final answer. So I think that's a good time for some critical notes. Copy these down, show them to me later so I know you watched the video. When we want to simplify the b root of x to the a, where a is greater than or equal to b, what we can do is divide a by b and get a quotient and a remainder. The quotient is going to come outside as a power, and the remainder is going to stay inside the bth root as a power. Now, sometimes when this simplifies all the way, like when there is no remainder, like in one of our first examples, you'll get x to the 0 here. And remember, that's just 1. And the root of 1 is just 1. This term will sometimes simplify if the fraction a over b would have reduced to an integer. Now, there's a lot of different ways that people will explain how this pattern works. And so I think it's good to at least see 2 of them. There's many more, but let's talk about this other perspective about pulling out pairs or threes of a kind, or multiples from inside the radical. Let's first substantiate it. If I have a divided by b, if we have a something greater than b or equal to b, then a is equal to b plus b plus b plus b q times, the quotient times, plus the remainder. Take a moment to digest this expression. A divided by b is equal to quotient remainder r, q remainder r. Then you can write a as equal to b plus itself q times plus r. Make sure that makes sense. Write down an example for yourself if it doesn't make sense. Now, in terms of exponents, because addition relates to products of the bases, that means that we can write x to the a as x to the b times x to the b times, and so on up to x to the b, q times, but then times x to the r. All of these timesings turn into plussings in the exponent. Now, what does that mean for us for our simplifying radicals question? Well, each one of these roots of b just gives me a single x. And so if I have something like the bth root of a, then I could rewrite a this way, or x to the a this way, as x to the b times x to the b, and so on, q times, and then x to the r. And each one of those, we can distribute the radical. We distribute the radical, and each one of those turns into a single x. X times itself, q times, that's what x to the q means. And this x to the r, well, the remainder is always less than the divisor. And so this cannot be reduced, and it stays just like this. So this is the formula that I put in the critical notes, but this is why it is. Now, let's tease some more out of this idea with a numerical example. We haven't really looked at just, roots and radicals of big numbers. How do we simplify the cube root of this fairly large number? Well, the main idea is we want to look at factors of 432. And since this index is a 3 here, we're looking for 3 of a kind. We're looking for a factor repeated 3 times that will pop out of that radical as a single factor. Let's see what I mean by that. Now, 432 is kind of big, though, so to list its factors, we might want to utilize a factor tree. So let's go over again how to make a factor tree. If you notice there's a divisor of this number, and I notice that 4 and 32 are both divisible by 4, so we could divide 4 into 432, and get 108. 4 times 108 is 432. Let's keep breaking these down, and we get 4 breaking into 2 and 2, 108 breaking into 4 and 27, and then just to complete things, we break this 4 down, 2 and 2 again, and 27, that's 3 threes. Let's just break that down in one step. Because really what's important here is the leaves of this factor tree. I want the prime numbers that we list on the bottom here. Now, there is 1, 2, 3, 4 twos, so 2 times 2 times 2 times 2, and then 3 threes, 3 times 3 times 3. So 432 is 2 times 2 times 2 times 2 times 3 times 3 times 3. Now, where do I see 3 of a kind? Because remember, we're simplifying the radical cube root of 432. Well, here is 2 cubed. We could bring 2 cubed out. The cube root of 2 cubed is just 2. So we bring out a single 2. Here I have 3 cubed. The cube root of 3 cubed is a single 3. So we can bring that up front too. And then what's left? Well, there's only 1 2 left over, and that gets stuck inside. That doesn't reduce anymore. And so we just kind of unite the 2 and the 3, and we get 6 cube roots of 2. This is another nice way to simplify radicals of, say, large numbers. We make a factor tree, we figure out how many of a kind we need to see, and then we pull out that many. That is to say, we put one copy of that factor up front for each, in this case, 3 of a kind that we saw. Okay, so here are some practice exercises for today. Try these and show them to me later. This will help solidify what I'm talking about in the previous examples. So I want you to try to simplify this quotient and this product. Pause the video and try that at this time. Okay, let's see how you did. So the first thing that I would do in simplifying 1 is to focus on each part separately using the distributive property. We can distribute the 4th root against each term, which I've color-coded for your convenience. And if we simplify them each in turn, 4 goes into 5 one time with a remainder of 1. 4 goes into 10 2 times with a remainder of 2. And 4 goes into 20 5 times evenly. And so what does that mean for our overall fraction? It means this one turns into x, 4th root of x. This one turns into y squared, 4th root of y squared. And this one just turns into z to the 5th. It's sort of nice to write the stuff that's in a radical back under a single radical and put the rest of the stuff out front. That's a nice way of looking at it. You could also put this into the numerator. This radical expression could also be under a single common quotient bar. That would be fine as well. As long as there's a product implied here, it's all good. So same trick for number 2. We want to not see this as one giant mess of a problem. We want to see this as 3 smaller problems by distributing. We distribute the 5th root against 192, against x to the 10, against y to the 22nd. Let's solve those each in turn. So 192 is again kind of a big number. I'm looking for 5 of a kind because this is a 5th root. So I split 192 down into a factor tree like this. Divide by 2, it's even. Divide by 2, still even. 48, I know the factors could be 6 and 8. And then splitting things up, we're done. Now, how many 2's do I see? 1, 2, 3, 4, 5, 6. So I can pull out 5 of them as a single 2. That comes out front. And one of them is stuck inside. Now, there's also a 3 stuck inside. I can't liberate that. So the 3 and the 2 are stuck inside as a 6. So the 5th root of 192 turns into 2 5th roots of 6. What about my 5th root of x to the 10? Well, that's x to the 10 fifths, or x squared. What about my 5th root of y to the 22nd? Well, that's y to the 22nd over 5, which breaks down this way. You could also see this. I mean, see if you could jump straight to it. 5, how many groups of 5 can I pull out of 22? I can pull out 4 of them. And then how many are left over still stuck inside? There's a remainder of 2. So that's another way of looking at it, another reason why this simplifies this way. Now we recombine things, right? We want to take a look at what they all are in product. So this one was 2 fifth roots of 6. This middle one was x squared. And this last one was y to the 4th fifth roots of y squared. We pull those things not in a radical up front. We combine those things still in the 5th root under a common 5th root, and we're done. That's it for this video today. Thank you for your patience and good luck with your studies. I'll see you in the next one.